Hello everyone, welcome to the fourth in a series of videos covering chapter 17. Today we'll be talking about the last section, 17.4, the Doppler effect. For all of you who have taken the subway, you may notice that the sound the subway makes when it arrives and when it leaves is interesting. Sounds like the movement, something about the shifting of the carts, sounds a bit different. But it's not actually that it's doing anything else, it's just that its motion has an effect on how you hear its sound. So, for example, you're chilling in the balcony and you hear a car alarm on the road. But you're just in the balcony, it's not your concern. The car owner, though, runs to their car and stops the alarm. And as they run, though, it appears that their alarm sounds a lot louder to them than to you, who is just chilling in the balcony. So, for an observer at rest, the frequency that they pick up from a source would just be equal to the emitted frequency of the source. And that's not the case when there's motion. So if you ever watch the Formula One racing, you'll notice a particular sound the engines make as they take a curve. It's like the sound gets really loud and a bit quieter, almost like a high frequency sound as they come towards the cameraman, and lower frequency as they shift away. Obviously, though, our ears or sense of hearing, it's not that we pick up frequency, we pick up pitch of sound. Our ears are not like straight up frequency detectors so much as they sort of transform the um, sensation of air vibrating in our ears with a certain frequency into signals that make us perceive pitch. Overall, when we talk about the Doppler effect, we're really just talking about the fact that our notion of pitch changes depending on whether or not there's some motion happening between the sound source and the observer. So, in the example that an observer is moving towards the sound source, then their observed pitch, their observed frequency will be bigger than what's being emitted. If the observer instead was, say, moving away from the sound source, the observed frequency would be lower. This cyclist here moving towards a car will actually hear a louder frequency than if they were standing still. And if this person were to move away from the car, then they would be receiving a lower frequency. This is because as the person moves towards the car, then they're receiving the sound waves, the crest of each sound wave, they're receiving them at a faster rate, so their notion of frequency is much, much faster. If they break away from the waves have to catch up to them. So since it takes longer to catch up to them, then the frequency of those waves, at least to the observer, is slower. Think of it as when you go swimming. If you want to catch some waves, you swim towards the wave so it hits you faster. If you're sick of swimming, you'll swim away from the waves so they have to catch up to you. Here's some cool GIFs. In the case that the sound source is moving, right, they're constantly producing this sound waves, these ripples outwards. And because they're moving to the left, each consecutive ripple is closer and closer to the left. So overall, all the waves are bunched up together towards the left. So a stationary observer will get a bunch of bunched up waves towards them, even though on the origin they're a little bit farther apart. So from the one side, the crests of the waves are closer together on the left. But if you're standing on the right, actually, the crest is farther apart. So here we see the observer now standing behind the car, and what they're seeing now, since the source is moving away from them, is that each crest that gets created, right, is now a little bit to the left, which means that there's a bit of a gap between consecutive crests on the right side. And that gap means that you see that from this right side, there's a bigger wavelength between crests, which means there is a smaller frequency. So you're standing on the right side of a moving car, you're going to hear a lower pitch. When the source moves towards an observer, then the frequency increases. And when the when the source moves away from the observer, then the perceived pitch decreases. to summarize all that, we have the Doppler effect, which is that description of how the perceived shift in frequency due to the relative motion of an observer and the source of the sound waves occurs. So when observer and detector, sorry, when source and observer are in motion, the emitted frequency and the observed frequency are different. And this is summarized in the Doppler shift formula here that accounts for both the motion of the observer here in the numerator and the motion of the source on the denominator. The speed here is the speed of the wave. So, in sound waves in air, this will be about 343 meters per second. And the signs in this function, to remember which one to use, is the mnemonic top sign is toward, meaning that when the observer is moving towards the source, then you use the plus sign because that will make the overall shift higher. If you're moving away from the source, then use a negative sign, meaning that the shift, there's a drop in frequency since you're moving away from the waves. And for the denominator term here, if the source is moving towards the observer, you're going to use a negative sign on top, since when you have a source moving towards the observer, the waves bunch up, so the frequency is higher. And when you have a source moving away, you will have the plus sign, which will overall make this smaller. Also, note that there should be a one more term here, which is the frequency, the original source frequency. So here we go. Sorry about that. So this is called the Doppler effect or the Doppler shift formula, since it tells you if the frequency shifts at all for the observer. Note that if there's no relative motion, if this term and this term are 0, then this whole parenthesis term is just 1 and the frequencies are the same. This, by the way, happens for all waves, not just sound. So this just has to do with how waves are emitted in this like ripple-like fashion, and how motion makes you receive waves sooner or maybe later. A cool example of the Doppler effect is in astronomy. We're not talking about the horoscope here, where the relative motion of the source and the observer can, shift the frequency, the observed frequency of starlight because they emit light. So when a star is moving away from us, its light appears to be redshifted. Its wavelength appears to be a lot bigger than it is, since when it moves away from us, its observed frequency drops, which means that since the wave speed is still the same, if the frequency is lower than the wavelength is bigger. However, though, if we have a star that is moving towards us, then its starlight is blue shifted, which means to say that the observed frequency of the starlight is bigger, and thus the wavelength appears shorter. So it's called blue shift because visible light that has a shorter wavelength tends to be a bluer color, and visible light with the longest wavelength is that of a redder color. Quick quiz, we'll have 3 detectors, and there's a ripple kind of moving in the middle to the right between all of them. And which of the following is true? So A says wave speed is highest at location A, B says the same about C, but the wave speed is constant. That doesn't change. Again, even if perceived frequency seems higher, then the perceived wavelength will be lower. The equality lambda f always holds because the medium's still the same. It's still air. So B says the detected wavelength is largest at location B. D says the same for C. So that's not true because A is farthest away and the ripple's moving away from A. So the crests are really far away when they hit A. So A has the longest wavelength. So C and D can't be. E says that detected frequency is highest at C. And this is true because the the source is moving towards C, which means that the waves are bunching up in its direction. So the C gets hit by the crests a lot faster than, say, A. So it's E. Okay, you stand on a platform at a train station and listen to a train approaching at a constant velocity. Well, the train approaches, but before it arrives, what do you hear? So if the train was still and you were still, you'd hear the same pitch that's being emitted from the train. When the train is in motion, then the pitch is shifted. If the train is in constant motion, though, then the pitch just shifts by a constant amount, and that's what it is for as long as the train is undergoing that same motion. So the frequency doesn't change before the train arrives. The frequency remains the same. It's shifted, but it doesn't change until it approaches the station and slows down. But the while the velocity during this portion then isn't changing for the train, it is still moving closer towards you, which means that the distance between you and the train is shorter, which means that the sound should be louder, it should be more intense. So we would go with option E. Okay, so one more thing to talk about is the fact that, well, any source of sound or waves, we've seen that waves are pretty fast. Even sound is a third of a kilometer per second. However, there's quite a few airborne objects and vehicles that can outrun the speed of sound. So that could be a bullet, that could be a fighter jet. And you can imagine then you have this source that's emitting this ripples of air particles, is emitting the sound waves around it as it flies through, but it's able to outrun its own ripples. It's able to outrun its own crests. So imagine here on the graph on the left here, this fighter jet emits a sound wave at this particular point, but then the jet, keeps moving really fast to the right. So as it does so, it outruns and surpasses its own crests of its emitted sounds. And as it's doing so, right, it's still emitting sound waves. So what this happens though, when you're able to outrun your crests, is that all the ripples you emitted align themselves along a sort of cone shape, and because you have all these like wavefronts basically forming this cone shape, this amounts to a lot of energy from all the wavefronts, creating a shock wave. And with some geometry, you can actually find out that the angle of the shock wave, so how big the shock wave actually is related to the ratio of how fast the airborne object is flying over the speed of sound. So I have this relationship here which says that the sine theta of the angle of the shock wave is equal to the speed of the bullet or the plane over the speed of sound. Basically saying that the faster the object is flying, the bigger the size of the shock wave, the bigger the cone. This assumes obviously that you're moving faster than sound. So when people talk about match speed, they're just saying about how many times is this flying object faster than the speed of sound in air. So a plane that achieves Mach 5 means that it can fly 5 times faster in sound. And here's a cool sort of like still frame of a bullet being shot through the air. Basically, what's happening is that the particles are slower than the bullet. So they are basically unable to really get out of the way of the bullet fast enough that it creates a shock wave. And so all the wavefronts that get sent kind of align in this shock wave, creating a very, very intensive wave of energy along the sides here, since it can't get out of the way fast enough. And you actually see shock waves in the ocean. If you're sailing on a yacht and you're going really fast, well, what happens is that your boat can be a lot faster than the speed of waves on water. So you'll create a similar effect where you're moving faster than the waves you create. So you're outrunning your own ripples, which basically makes the waves kind of combine together into this like shock wave, this conical shock wave behind you. That's again an amalgamation of a lot of waves. So it's a very powerful wave altogether. And it's something similar that happens not in the water, but in the air with jet airplanes, where they're traveling really fast, so they create this trail of shockwaves behind them. And these are not just powerful waves of water, these are powerful sound waves in air. And powerful sound waves are capable of destroying many structures and glass. And we call that a sonic boom. So the hopeful thing is that if a jet airplane moves that fast, that they'll be up in the air away from a lot of structures, because otherwise the sonic boom can cause a lot of property damage and hurt everyone's ears. So hopefully no jet plane flies low altitude. Also, one more bad news about it is that the shock wave kind of begins at the nose of the airplane, and because an airplane has both a tail and a nose, both effectively noses, right, nose shape, and they're both also moving really fast. Even though one's kind of pointing the other way, they're both moving faster than sound, so they both create this ripples of air and create this shock wave from both sides, where air can't run away fast enough that you end up with double shock wave and an impressive sonic boom. And that's all for the content of the chapter. So one more quick quiz. An airplane is flying with a constant velocity, moves from a cold air mass into a warm air mass. What happens to the Mach number? Okay, so remember the Mach number is just the ratio of the plane speed over that of speed of sound in air. And we saw that in warmer climates, air is less dense. Speed of sound in hot air is faster than in cold air. So that means that in warm air, the speed of sound is bigger, and Mach speed is the speed of the plane over the speed of sound in air. So the speed of the plane is the same, the speed of sound has increased, which means that the Mach number in hot air decreases. Well, that's it for chapter 17. I hope you join me next week, where we'll be talking about waves per position. Until next time, have a good day.